Hello everyone, and welcome back to Tech Adventure. I hope you're doing well and staying focused on growing your skills in software development, interview tips, and embedded systems. In our previous videos, we covered the top 50 real C and C++ interview questions and explored the solid principles and design patterns. If you missed those, I highly recommend checking them out. They provide a strong foundation for what's coming next. As promised, we're now moving ahead with key topics like RTOS and microcontrollers. Today's focus is on RTOS. This video covers the most frequently asked RTOS interview questions based on real interview experiences. You'll get clear, in-depth answers to key topics like task scheduling, semaphores, mutexes, ISRs, context switching, and more, explained simply and practically. Whether you're a fresher or an experienced engineer, this video will help you understand the core concepts, avoid common mistakes, and confidently tackle technical interviews in embedded and real-time system roles. Don't forget to like, comment, and subscribe for more embedded systems content. I've previously created a video on essential skills for embedded engineers, where I explain key RTOS concepts. I recommend checking it out first for better context. You can find the link in the description or in the I button above. Let's dive in Q&A. 1. What is an RTOS and how is it different from a general-purpose OS? A real-time operating system, RTOS, is a special kind of operating system designed to process data and events within a guaranteed time frame. That means it responds predictably and quickly, which is critical for time-sensitive applications like automotive control systems, example, airbags, ABS, medical devices, example, pacemakers, ventilators, industrial machines, drones and robotics, IoT devices. The goal of an RTOS is not high throughput, like in desktop systems, but determinism, being able to guarantee that certain tasks will run on time, every time. On the other hand, a general-purpose system like Windows, Linux, or Mac OS is designed for general computing tasks such as browsing, gaming, and office work. It focuses on maximizing throughput and user experience, not necessarily on timing precision. Here is our RTOS versus GPOS. Easy comparison table. Have a look. 2. What are the main components of an RTOS? An RTOS is made up of several core components that work together to manage tasks, time, communication, and resources in a predictable, real-time manner. Here are the main components of an RTOS. 1. Task or thread manager. This is the heart of the RTOS. It creates, deletes, and manages tasks, also called threads, which are individual units of work. Each task has its own stack and priority. Tasks can be in states like running, ready, blocked, or suspended. RTOS manages multitasking so many tasks can run simultaneously via fast switching. Example, reading sensors, updating display, and communicating over UART can all be separate tasks. 2. Scheduler. The scheduler decides which task runs next based on priority and scheduling policy. Preemptive scheduling. Higher priority task interrupts a lower priority one. Round robin. Tasks of same priority share CPU time. Deterministic. Ensures time-critical tasks run on time. Think of it as a referee managing a queue of players, tasks, deciding whose turn is next. 3. Interrupt service routines, ISRs. ISRs handle hardware interrupts. Example, a timer tick, a button press. It should be very short and fast. Often used to wake up tasks or signal them using semaphores or queues. Avoid complex logic in ISRs to keep the system responsive. ISR. Hey, something urgent happened. Wake up the right task. 4. Inter-task communication, IPC. Tasks need to talk or sync with each other. RTOS provides IPC mechanisms like semaphores, signal between tasks or ISR to task. Mutexes protect shared resources, example, UERT. Queues pass data, example, sensor value from ISR to task. Event groups signal multiple flags or events, like giving a note, queue, or raising a hand, semaphore, to signal another task. 5. Timers. RTOS provides software timers for tasks that need to run after a certain delay or periodically. Useful for timeouts, periodic actions, like blinking LEDs. Based on the RTOS tick timer. Example, restart motor every 500 milliseconds using a timer. 6. Memory management. The RTOS manages memory for task stacks and dynamic allocation, if used. Static allocation, recommended, memory assigned at compile time. Dynamic allocation, use of heap, can cause fragmentation if not managed well. Think of it as organized shelf space for each task's workspace. These RTOS components can also be asked as separate questions, like, what is a task? Or what is a scheduler? Understanding them now helps you answer confidently. 3. What is the difference between a process and a thread? A process is an independent program in execution. It has its own memory, code, data, and system resources. Processes are isolated from each other. One process cannot directly access another's memory. Example, opening two separate apps like Chrome and Word starts two different processes. They don't share memory or variables. On the other hand, a thread is the smallest unit of execution within a process. Threads in the same process share the same memory and resources, but each thread has its own stack and program counter. Example, in Chrome, opening multiple tabs runs multiple threads. They share browser data, cookies, cache, but each thread runs independently. Here are the key differences. Process versus thread. Have a look. 4. What is context switching in RTOS? Context switching in an RTOS is the process of saving the state, context, of the currently running task, nothing but processes, and loading the state of the next task that is about to run. This allows the CPU to pause one task and resume another, creating the illusion of multitasking. Even on a single-core microcontroller, it is needed. In real-time systems, multiple tasks run simultaneously, but since only one task can use the CPU at a time, the RTOS must switch quickly between tasks to meet timing deadlines. During a context switch, the RTOS saves. Program counter, what the task was doing. CPU registers, temporary data. Stack pointer, task's local memory. Status registers, flags, mode, etc. Then it loads the same data for the next task, so that task resumes exactly where it left off. 5. What are the types of scheduling in RTOS? Scheduling is the method the RTOS uses to decide which task should run next. Since only one task can use the CPU at a time, on a single-core MCU, the RTOS must manage the order efficiently, especially in time-critical applications. Here are the main types of scheduling in RTOS. 1. Preemptive scheduling. Most common in real-time systems. The RTOS can interrupt a running task if a higher priority task becomes ready. Ensures high-priority tasks run immediately. More deterministic, but requires careful design to avoid priority issues, like starvation. Example, in a smart home system, a sensor reading task, low priority, is running. Suddenly, a fire alarm interrupts makes a fire safety task, high priority, ready. RTOS preempts the sensor task and switches to the fire safety task immediately. Think of it like giving way to an ambulance, high priority, in traffic. 2. Cooperative scheduling or non-preemptive scheduling. Tasks voluntarily give up the CPU. Tasks run until they voluntarily yield, give up control to the RTOS. Simpler and uses fewer resources. No preemption. If a task gets stuck, it blocks others. Example, in a small IoT device. Task A, example, blinking LED, runs and after completing, it give control to task B, example, read temperature. If a task doesn't yield, others are starved. 3. Round-robin scheduling. Equal priority tasks share CPU in time slices. Tasks with the same priority get equal CPU time, one after the other. Works with time slicing quantum. Common for background or low-priority tasks. Example, in a data logger. Task A, log to SD card. Task B, display data. And Task C, send over UERT. All have the same priority. RTOS gives each a small time slice, example, 10 milliseconds, and then switches to the next. 4. Rate monotonic scheduling, RMS. Priority based on how often the task runs. Shorter period tasks get higher priority. It's a static priority algorithm, good for periodic tasks. Assumes tasks don't block each other and meet deadlines. Example, Task A, updates LED every 10 milliseconds, high priority. Task B, logs data every 100 milliseconds, lower priority. RTOS always favors the more frequent task, LED, ensuring smooth blinking. 5. Earliest deadline first, EDF. Task with the nearest deadline runs first. Dynamic priority scheduling based on deadline. More flexible and efficient than RMS, but more complex. Often used in advanced RTOS or soft real-time systems. Example, Task A must finish in 20 milliseconds, Task B in 50 milliseconds. Even if B started earlier, A will run first because its deadline is closer. And that wraps up our session on RTOS. An RTOS includes more features like interrupt handling, timers, and inter-task communication via semaphores, queues, etc. to keep tasks synchronized and efficient. In short, an RTOS is all about speed, reliability, and timing precision, ensuring critical tasks never miss a deadline. We'll continue this topic in our next video with a more interactive format, featuring real interview-style questions and answers. We'll dive deeper into key RTOS concepts such as semaphores, mutexes, inter-task communication, and critical sections. If you found this video helpful, don't forget to like, share, and subscribe for more content on software development, interview tips, and embedded systems. Also, I encourage you to subscribe to my other channel. The links are in the description. Stay curious, keep learning, and see you in the next video.